Hey everyone, welcome back. So, we hear about AI literally everywhere these days, right? It's drafting our emails, summarizing our endless meetings, even writing code for us. But today, we're going to do something really fun. We are going to peek right beneath the hood of tools like ChatGPT and other massive AI models to see how they actually work. And don't worry, we are doing this without getting bogged down by any heavy mathematics. We're keeping it clear, keeping it visual, and just focusing on the mechanics that drive the magic.
You know, when you're chatting with an AI, it feels incredibly human. It really feels like it's pondering your question and forming a conscious thought. But today, we need to act as the wizard behind the curtain and shatter that illusion of sentience. Because at its absolute core, these systems are not thinking the way you or I do. They are basically engaging in a highly complex mathematical guessing game.
Okay, let's dive into this. Here is our roadmap for today's explainer. First, demystifying large language models. Then, embeddings, mapping meaning. Third, we'll look at the context window bottleneck. Fourth, giving AI external knowledge. And finally, evaluating the AI competitors.
Starting with Section 1, demystifying large language models.
So, what is actually happening mechanically when you press enter on a prompt? Despite the seemingly magical outputs we see every single day, these systems are fundamentally built on something called statistical language modeling. At its essence, the system computes a probability distribution over a massive vocabulary of tokens, which, by the way, are just words or parts of words. It looks at the text you gave it, scans its vast vocabulary, and simply tries to predict the most statistically likely next token. It's an autoregressive process, which just means it generates one token, feeds it right back into itself, and guesses the next one, over and over again.
Let's walk step by step through the literal journey of a single prompt. First up is tokenization. This is where your raw text gets chopped up into those smaller chunks or tokens. Second is embedding. These tokens are mapped into high-dimensional vectors. Essentially, we're turning words into numbers. Third, and this is where the heavy lifting happens, the transformer architecture uses what's called an attention mechanism. It looks at all the tokens and figures out which ones are the most important relative to each other. Finally, output generation. It calculates raw scores, called logits, pushes them through a function to turn them into probabilities, and just picks the winning token to output back to you.
Moving on to Section 2, embeddings, mapping meaning.
Now, you might be wondering, how do you actually turn human language into math? Well, an AI maps out meaning by treating words as coordinates in a massive multidimensional space. But here's the kicker. Modern models don't just use simple static definitions. They use contextualized embeddings. This is a huge breakthrough. It means a word doesn't just have one static mathematical definition. Its actual coordinate in that massive space shifts and changes based entirely on the neighboring words surrounding it in your sentence.
And this brilliantly illustrates the concept. Look at the word bank. If you say sitting by the riverbank, the AI uses its attention mechanism to see the word river. Geometrically, the embedding for bank shifts over to a location in its mathematical space related to nature and water. But if you say depositing money at the finance bank, the AI sees money and finance, and suddenly the word bank is represented in a completely different coordinate related to economics. It's literally understanding context geometrically.
All right, Section 3, the context window bottleneck.
If the AI is so incredibly smart at reading context, why can't we just feed it an infinite amount of text? Like, why not just drop an entire library of books in there at once? Well, we run into what researchers call the context stuffing problem. Models have a fixed context window, basically a hard limit on how many tokens they can remember at once. And studies actually show that if you just flood an AI with massive amounts of unfiltered information, treating it like a giant haystack, the answer quality actually decreases. The AI struggles to find the needle of valuable facts, and the risk of hallucination, where the AI just completely makes things up, increases dramatically. So more noise definitely doesn't mean better answers.
And there's actually an even bigger hurdle here, the cost. The transformer architecture has what's called quadratic computational complexity. That's a fancy way of saying as you increase the sequence length, the compute power you need skyrockets exponentially. To put that into perspective, training a model like Llama on a standard 2,000 token context costs roughly $3 million. But if you wanted to train it on a massive 100,000 token sequence, the cost would balloon to an estimated $150 million. That is no small change.
Now, we are starting to see ultra-long context models pop up, like Gemini Pro 1.5, which boasts a 1 million token context. But feeding that much context into a prompt costs roughly $7 per query, That is incredibly expensive for everyday use, so the crucial point is comparing that with RAG, or Retrieval-Augmented Generation. With RAG, you only retrieve and pay for the specific, highly relevant tokens you actually need. RAG offers massive cost savings, potentially reducing costs by up to 99%, all while keeping the AI laser-focused.
Let's look closer at that in Section 4, Giving AI External Knowledge.
So if we can't affordably stuff the prompt with everything, and we obviously can't afford to constantly retrain the model on new data, how do we keep the AI smart and up to date? The answer is RAG, Retrieval-Augmented Generation. Instead of relying on the AI's internal static memory, RAG connects the AI to an external database, like your secure company wiki or a library of PDFs. When you ask a question, the system first searches the database for the exact facts, retrieves them, and secretly slips them into the prompt for the AI to read. It's essentially giving the AI an open book exam, so it can look up the exact facts before it answers, and that severely limits those pesky hallucinations we talked about.
Think of human memory kind of like the classic butcher on the bus analogy. You see someone on a bus, and your fuzzy, flexible memory recognizes their face, but you just can't place them. It takes a moment before your specific, discrete memory kicks in and says, "Aha, that's the local butcher." Large language models are just like that fuzzy, creative memory. Knowledge databases are the static, reliable facts. By combining them using RAG, we create a perfect, highly reliable working memory.
To sum that up, RAG is like taking an open book exam. It's how you give the AI factual, access-controlled, timely information. Fine-tuning, on the other hand, is like studying for the exam. Fine-tuning actually updates the underlying weights of the model. You don't generally use fine-tuning to add new facts. You use it to adapt the style, the tone, and the linguistic vocabulary of the AI so it speaks exactly how you want it to.
Let's wrap up with Section 5, Evaluating the AI Competitors.
With a new model dropping seemingly every week, how does the industry actually judge who is winning the AI race? Because, let's face it, there is no single perfect mathematical metric for intelligence. So we rely on a diverse mix of leaderboards. We have automated mathematical benchmarks with fun names like Blue and Rouge, which measure the exact n-gram overlap between what an AI generated and a reference text. We have MTEB for testing embedding quality, but increasingly we rely on the chatbot arena, which uses a crowdsourced ranking system based on blind human preference votes. It turns out human vibes and automated exactness are both totally necessary to get a full picture. Now what's really interesting about this slide is looking at the actual human evaluation data. Here we have Meta's open-source Llama 2 going right up against OpenAI's proprietary ChatGPT. In this helpfulness evaluation, Llama 2 won 36% of the time, tied 32% of the time, and lost 32% of the time. This proves that open-source models, whose weights are freely available to anyone, are genuinely going head-to-head with massive closed-source proprietary giants. The gap is closing incredibly fast.
I want to leave you with this final, kind of provocative thought. We talked a lot today about the current context window bottlenecks and the high costs. But as techniques like flash attention advance and context windows scale to millions or even a billion tokens, the whole paradigm might shift again. Will we still need complex retrieval-augmented generation setups? Or will future AIs simply ingest your entire company's history, or perhaps literally everything ever written on the internet in a single instant before answering your prompt? The frontier of machine learning is moving at lightning speed, and I really hope today's explainer gave you the foundation to understand whatever comes next. Keep exploring, keep questioning, and I'll see you in the next explainer.